So now let's move on to dimension reduction. So this is another topic in unsupervised learning, or another types of algorithm in unsupervised learning. So among the variables in the data set, some variables may carry very little information that is relevant to the task at hand. And some variables are informative but are redundant. Namely, two or more variables are giving essentially the same information, right? For example, if you have a variable that is height, that is for example, that is the height in inches. And you have another variable which is height in centimeters. Suppose both of them exist in your data set. Then apparently one of them is completely redundant because they have a perfect linear relationship. The information contained in one column is completely contained in the other column. So one of them is totally useless. So how to control redundant or irrelevant variables? And why do we need to control them? There are multiple reasons. So first, redundant variables make it harder to learn from data because irrelevant variables are simply noise that obscures actual patterns. If you have two variables, x1 and x2 are very similar, not exactly the same, but very similar, then the difference from them is basically noise. Maybe due to measurement error or because of some other reasons that there is a difference somehow. The difference is noise. And because they are highly correlated, it will introduce a big variance in the data set. And then for machine learning algorithms, a large number of variables will present computational challenge. That's right. Yeah. For high dimensional data, the searching surface is very bumpy because if the dimension is very high in your searching space, then it's very likely that your training data set is very sparse. Namely, the distance between any two observations is very far away. In that case, you can imagine if you have a new observation, it's very difficult to do a very good prediction. And also the algorithm itself is very difficult to converge just because the searching surface is too bumpy. So all of these motivate us to reduce the dimension. So let's first take a look at the iris data set. So it has 4 feature variables, the length and the width of sepals and petals in centimeters. Let's take a look at the relationship between petal length, petal width, and sepal length. The first scatter plot shows you the relationship between petal length and petal width. So there is a very strong linear positive relationship between petal length and petal width, which means the information that is contained in one variable is also contained in the other variable. And also petal length and sepal length, there is also a moderately strong linear relationship between these two variables. So from this 2 scatter plots, we know that the variables in the average data set are highly correlated, which indicate that some variables are redundant. They may not be necessary in building a model. We actually have seen this before. We use all of the variables to create a decision tree, but in the end, only 2 variables are used. okay, and two variables are not used at all, were not used at all, right? That's because those two variables are not necessary. Okay? They're redundant. So the strategy we use to reduce dimension is principal component analysis. So this strategy uses an orthogonal transformation to convert a set of observations of possible correlated variables into a set of values of linearly uncorrelated variables called principal components. So basically, we create some new variables using existing variables. And each new variable is a linear combination of our X variables. So let's first take a look at some notes about this algorithm. So first, how many new variables can we create? If there are n observations with p variables, so our data matrix suppose is like this. So n rows and p variables. Then the number of distinct principal components is the minimum of n minus 1 and p. By the way, the principal components is a linear combination of all variables. So this is a new variable, right? So don't be confused. It's just a new variable. So the number of distinct new variables is the minimum of n minus 1 and p. So usually, n is greater than p, right? Usually, there are more rows than columns, right? For regular data set. In this case, you can create p distinct principal components. P distinct principal components. But if n is smaller than p, smaller than or equal to p, then you can only create n minus 1 principal components. So that is because the number of distinct principal components depends on the overall degrees of freedom in the data set. So that is usually the smaller dimension of the data set. And let's continue. The first principal component has the largest possible variance, or in other words, it accounts for the largest proportion of variability in the data. So it contains the most information, the most amount of information in the data set. And each succeeding component in turn has the highest variance possible under the constraint that it is orthogonal to the preceding components. So let me use a plot to show you this idea. Suppose we have a data set like this. A cloud of data like this. This is X1, so two-dimensional data. Then consider we want to project the data to a one-dimensional space, to a line. Then we need to pick a direction such that the variation of the data is maximized. Okay? It retains the most variability in the data set. From this plot, it's very obvious that the best direction is this one. So if you project our data to this line, then they will be like this. If we use a rock plot to show it, it looks like this. So apparently, the observations on this line has the largest variance or spread. So this will be called the first principal component, the first principal component. And then we need to find another direction such that the projected observations has a second largest variation, or it explains the second largest proportional variability in the data. And another restriction is it has to be orthogonal to the first principal component, first direction. So since we only have two-dimensional data, we have no other choice. So the other direction must be this. And if we project our data to this direction, we have a rock plot like this. Okay? And they must be orthogonal. Orthogonal. So this is PC1, and the green one is PC2. And apparently from this plot, we see that both PC1 and PC2 are linear combinations of x1 and x2. Right? And they are orthogonal with each other. And PC1 always explains the most proportion of variability, and PC2 explains the second largest proportion variability. If we have more than the first, so the amount of variation explained is always in this order. And the last one is the least important one. So it's always like this. Okay. And the resulting vectors are an uncorrelated orthogonal basis set. Okay. So the other new variables, the principal components, are uncorrelated. Okay. And from this calculation, you know that PCA is sensitive to the relative scales of original variables. Okay. Consequently, we usually need to scale the data first, right, before we apply the PCA algorithm. Okay. So apparently, principal component analysis is useful in dimension reduction. It also, in particular, is often used to do visualization, right? Because we only can have 2 or 3 dimensions. If we want to create a plot, right, we can only use 2 or 3 variables. So it's widely used in data visualization. Now let's examine some details of principal components analysis. The PCA creates new variables, PC1, PC2, etc. And each variable is a linear combination of existing variables. For example, take a look at PC1. It can be denoted as phi11x1 plus phi12x2 all the way to phi1pxp. So notice that each coefficient, each slope has 2 subscripts. The first subscript is corresponding to the index of the principal component. Now we see 1, 1, 1, 2, 1p. And the second index subscript is corresponding to the x variable, the index of the x variable. So from this, you know that for each principal component, we have a set of slopes. B I1, B I2, all the way to B I P. Yeah. And the algorithm actually will return this vector of coefficients or slopes. Right? And in order to define a unique vector for each principal component, we require that each vector of coefficients or slopes has norm 1, namely sum of phi1j squared has to be equal to 1. Sum of phi squared must be equal to 1. Right? Otherwise, if we only consider direction, right, it's not unique. Right? The direction only describes the relationship between x1, x2, all the way to xp, but it's not unique. Right? But by restricting, put a restriction like this, the principal component is kind of like fixed, right? Somehow fixed, or you can say it's unique, along each direction. So geometrically, PCA amounts to a rotation of the coordinate axis, so that more of the variability can be explained using just a few variables. So in the previous example, in the plot, I show you the two principal components are like this and that. Okay. If you rotate the entire data using, namely, if you let PC1 be parallel with the x-axis and PC2 to parallel with the y-axis. Okay. It's essentially a rotation of the coordinate system or the axes. And then you can choose to discard some principal components. For example, in this case, we may choose to discard the second principal component because it's relatively smaller. And suppose we only want to use one-dimensional data, okay, then we can get rid of PC2. And PCA is an example of linear dimension reduction, okay, because you see each principal component is a linear combination of X variables. All right, let's take a look at the iris data set. As I said, we need to scale the data, right, because the distance is sensitive to the magnitude of variables. Not the distance, is the calculation of the slopes in the principal components is sensitive to the magnitude of variables. So let's deselect species, the response variable, and apply the principal component function PRComp. So this function is a base R function actually, and then specify scale equals true. Then the data will be scaled. And then take a look at the rotation component in the result. Okay, we see the result in PC iris. So these are actually the coefficient matrix. Okay, the slopes. Okay, the slopes for each variable. Okay. So for example, PC1 is equal to 152. So this one times sepal length, and this times sepal width, this times sepal petal length, etc. Right? And then given the values of one observation, sepal, given these values, then PC1 has its own value. Right? So namely, is a complete transformation of the original data set to a new data set. So originally we have four variables, right? X1, X2, X3, X4. And we have a lot of observations from 1 to 150, for example, for the iris data set, right? And after we apply the PCA function and calculate the principal components, we will still have four principal components. So four new variables, still 150 observations. Okay, just each variable is a linear transformation of the previous variables. Okay. And now all of these principal components are orthogonal with each other. They are all uncorrelated. And also they are ordered in terms of importance. PC1 is the most important, and then PC2, etc. But all right, let me see what else. Okay, then let's see the result. So let's plot the first two principal components, okay, for the iris data set, and we map species to color. So you see, this is the true labels and the first two principal components. And for comparison purpose, we also map the clustering labels to the plot. So you see the difference between the true labels and clustering labels. But anyway, so this example shows you that PCA is a strategy to reduce the dimension of data and create visualizations. Okay. All right. I think I will stop here because the next example is a more advanced example, and we only have 4 minutes left. I will continue tomorrow. And I will email you about your quiz 4. The last quiz is still about supervised learning. There's nothing about unsupervised learning. However, your exam 2 will cover unsupervised learning. So I suggest you to practice all of these examples and make sure that you are familiar with these algorithms as well. All right, any questions? All right, hello everyone. Welcome to today's class. Today we will finish the last topic, principal component of analysis in the last module, unsupervised learning. And we will see another example of clustering. Use clustering strategies to solve a problem in practice. Okay. Let's see. Principal component analysis. The last time we introduced this method. So this PCA is used to reduce the dimension of a data set. Okay. So basically, this PCA analysis will create new variables using existing variables in the data set, X variables. And those new variables are linear combinations of existing X variables. And the principal components, each variable is called a principal component. So I will label them in this way, PC1, PC2, etc. Okay. And if there are n observations in the data set and p variables, and then we can create the minimum of n minus 1 and p distinct principal components using the data set. It really depends on which number is bigger. Okay. And so suppose p is smaller than or equal to n minus 1, then we can create these many principal components. Okay. Each one is a new variable, which is a linear combination of existing variables. Okay. And they are ordered in terms of importance. Right? Namely, the first principal components contains the most information in the data set, right? The most amount of information or percentage of information in the data set. And then the second principal component contains the second largest amount of information in the data set, etc. And the last one contains the least information. Right? And also, all of these principal components are orthogonal or uncorrelated. So they are just geometrically orthogonal with each other, right? The directions. Okay. And the last time we talked about the construction of principal components. So each principal component is a linear combination of X variables. Okay. And also the coefficient vector is normalized, which means the norm is equal to 1. So this is another restriction about principal components. So let's see another example. This data set. Yeah. So both from Scottish Parliament. So this is a very wide data set after data transformation. So consider votes in a Congress in the Scottish Parliament in 2008. We know that legislators often vote together in some pre-organized blocks, for example, political parties. And thus the pattern of A's and Nays on particular ballots may indicate which members are affiliated. So this is kind of an expectation. We know that politicians vote according to their public the party, a political party usually. And let's take a look at the data set first. We can use this structure function to take a look at the overall structure of the data frame. So it has 103,000 observations about, and the three variables only. The first variable is the bill, the name of the bill. And the second variable is the name of the legislator. And the last one is the vote, either 1 or 0 or -1, which represent yay or nay or abstain. There's three values. So this is actually a very long, very narrow data frame originally. However, suppose we want to answer one of the following questions. For example, can the members of parliament be grouped according to their voting patterns? So if we answer this question, we want to answer this question, then the unit should be each member in the Congress. In other words, each row should contain all the information about one legislator. Apparently, our original data set is not like that. So each row is corresponding to the voting result of one person on one bill. So consequently, because each person will vote on all the bills and there are many bills, so this is a kind of this is in a different structure. So in order to answer our question, we need to transform this data set into a wider data set. Namely, we want to make it wider and so that each row represents or contains all the information about one legislator. In order to do so, we can use the spread function in the tidyr package. We have learned this before in the data wrangling module. So we can take the votes data set, the original data set, and apply the spread function. And we will use the values in the bill variable as new variable names. So use it as a key variable. So each bill will have its own column. And the vote variable will provide the values in the new table. And so basically 1, 0, or -1. And then make it a table. And after the transformation, we name the data frame y.votes. Now take a look at the dimension. So now it only has 134 rows and 774 columns. So it's a wide data set now. So this is the number of members in the Congress. And there are 773 bills. The first variable is the name of the legislator. So take a look at the first few rows of the data set, of the wide data set. So each row is corresponding to one person, and the column name is the bill, the name of the bill for all of the 773 bills. Okay. And in this case, if we want to use PCA to reduce dimension, the question is how many distinct principal components can be created using this data set. So remember, the rule is we can create the minimum of n-1 and the p distinct PCs, right? So now n is apparently smaller than p, so we actually can create 133 distinct principal components instead of 773. And we can only create these many principal components. Okay. All right. So before we start, let's create a tile plot to see if there is any pattern in the data set. The x-axis is corresponding to different ballots or the different bills. and the y-axis is corresponding to different members of the parliament. So apparently there is no pattern. I cannot tell any difference, any pattern from this flat. It's kind of like a carpet. And how about PCA? PCA can be used to create visualizations, can be used to reduce the dimension and then create visualization, right? So let's try to use PCA to reduce dimension to 2 and then see if we can figure out how many clusters are in the data set. So we'll first remove the name column and then scale the data, although it is not really necessary in this case because all of the values are 1, 0, or -1. So it's not really necessary, but anyway, it doesn't hurt. Right? Save the result here. And then, so since we didn't specify how many components we need, it will actually create 133 principal components for us. And then let's select the first 2 principal components and the name from the result. By the way, the X component of the output of this function contains the principal component values, the values of the new variables. So previously, last time, when we did an example using the iris dataset, we only took a look at the rotation. The rotation contains the coefficients, those Vij's in the formula, the coefficients. For example, so this is the first 10 coefficients of the first principal component. You see the first column, rotation, first column, the first 10. So totally, actually, there are 133 Vij's, right? Totally 130. Yeah, because we have, no, sorry, actually not 133. Actually, there are 733. Yeah, 700. See, sure. 773 Vij's. Okay, 773 Vij's actually. Okay. For each principal component. Okay, we just show the first 10, okay, for the first principal component. And these are the first 10 for the second principal component. Okay. And the X matrix actually contains the values of those new variables or principal components. Right? So see, we pull out the first 2 principal components, right, and show the first 6 values. And then let's create a scatter plot using the first 2 principal components. So it looks pretty good. We can see clearly at least 3 clusters in the data set. Okay, 1, 2, 3. Potentially there are more clusters over here. Okay, so apparently the voting results are clusters according to something unknown, okay, for us yet. Okay. And let's first use k-means, the k-means method to cluster the data. For example, we know that there are 6 public parties in the country, the 6 national Scottish political parties in the country, but there is one more small party somehow. So totally, we will use 7 centers in the k-means function. And then we create a new variable called cluster. So this one contains the clustering labels. And then use a mutate function to add it to the principal component matrix. And then we'll create this scatter plot. Map color, the clustering label to colors. As you can see, pretty good, the result. Okay. So, which means the clusters are kind of, we can actually visualize those clusters using the scatter plot. And then let's compare the clustering labels with their true parties. So actually, we have a separate data set which contains the party information of all of the legislators, right, that is contained in this data set called parties. Right? So we can mutate, right? We can use the left join to join these two data sets. One is the rows data set, and the other one is the party data set, by name. And then we create a contingency table of the clustering labels and the true party status. Of course, we know that the clustering algorithm does not know the ground truth, so it can never assign true labels to those observations. It will only assign integer numbers. So you cannot just focus on the diagonal of this contingency table anymore, right? Instead, we just focus on each row and see whether or not most of the observations are clustered into one column. Right? And if that is true, then the program is good, right? The algorithm is good. Right? For example, take a look at this party, Scottish National Party. So 35 out of 36 members are clustered to cluster 1. Similarly, this one, 15 out of 17 is clustered to the fourth cluster. So the result is pretty good, pretty good. Although, remember, the k-means method is an unsupervised learning algorithm. It does not have any information about the target value, but the clustering result is good. So the expectation is true. Those politicians actually vote based on their party. Yeah. Basically, they vote in blocks. And then how about so let's see. Suppose we don't know how many clusters we need. Let's see how many clusters we need using the first 10 principal components. Of course, we can just directly feed the entire data set into it, but it might not be a very effective or efficient idea. So let's just select the first 10 principal components and save it in PC10, and then use this function to identify the optimal number of polys, clusters. So turns out that optimal k is equal to 5. Although actually there are 7 different parties. But from this table, you see that some parties are very, very small. So you see the first one only has 1 member, and the third one also only has 1 member, and the last one has 1 member. So basically these 3 are either outliers, or the algorithm, the function probably put them together or put them into some other clusters. So optimal is 5 based on this gap statistic. And then let's fit a k-means model using center equals 5. Then we have, this is the result. And supervised, actually principal component analysis can be used in supervised learning models. They can be used to pre-process the data apparently. Those to reduce the dimension of a very wide data set. And then we can feed those, the first few principal components into a supervised learning model and do prediction for the y variable. So for example, let's fit the decision tree model on the both data set. So we first do the following. We select the first 10 principal components, and then save it here. And then we will just use it to put a decision tree. We call it votes.data. And then we split the data, okay, to a training and a test set, and feed the decision tree using a training set, and then calculate the misclassification rate for the test set. It turns out that the misclassification rate is very small. It's about 7.4%. Okay. So this means actually the first 10 principal components contains a lot of information. Right? Uh, there are actually, remember, actually there was 773 columns, right? Except for the first column, there are this many columns. Right? And we reduce it to 10 columns and then use it to fit the decision tree model. The result is pretty good. All right. This is how to use PCA in the supervised learning model. So you can use it to reduce dimension. And then another very important topic. We know that after transformation, each principal components contains a certain percentage of variation in the original data set. And they are ordered in this way. PC1 is greater than PC2, is greater than all the way to the last one. In the sense that the first one contains the most information, the second one contains the second. And how to calculate this kind of percentage or level of importance. So actually the plot, this function, the PR comp function, actually returns some quantities or statistics that can help us to calculate that. In particular, it is a standard deviation component. So this one sort of contains a standard deviation for each principal component. Suppose for our both data set, we can create 133 principal components, right? And then this vector SDEV will contain 133 values. It's a vector of this length, 133. And then we square it and then divide it by the sum of it. We can, so this quantity is called proportion of variance explained. Proportional variance explained. Right? Because we sort of normalize it, the sum of them, the sum of PVE is equal to 1. This factor is equal to 1. And let's take a look at the first 10 principal components, the PVEs. So you see the first principal components contains about 53% of the information or variation or the variance in the data set. And the second component contains about 20% of the information. So if you add them together, so the first two principal components contains about 73% of information already. And this PVE decreases along the index. And so first 10 add together, it's a lot already. And we can actually visualize the PVE, the change in PVE. So this is the plot is called the streak plot. It's kind of just like a scatter plot, connect the scatter plot for the number of principal components, the principal component index, and PVE. For example, this is a plot for the discrete plot for our votes data set. And of course, there are actually 133 principal components. We can create a very large, very wide plot. But because we know that only the first few principal components contain most information, so we just pull out 15 of them and create a plot so that each point is bigger. And notice that at a certain point, PVE dropped a lot, right? Which means the PVE of a certain principal component suddenly dropped a lot. For example, PVE4, compared to PVE2, PVE3 is significantly smaller. So this point usually is called an elbow in the screen plot. So this indicates probably the optimal number of principal components you need. But it's not necessarily, it is not always true. Okay, pay attention to that. So let's see, you see PVE3 is only 2%, 2.3%, and PVE2 is still 20%. So indeed, there is a big drop at 3. So this is where this elbow is located. Okay. But this can use as a reference, but it may not be very precise. It may not always be very reliable. So pay attention. A more reliable way to visualize the result is to create this cumulative proportional variance explained plot with this kind of plot. Yeah. So for example, so let's enlarge the x-axis. We can consider the first 50 principal components. So now we put out the first 50, and PC is from 1 to 50. And then we create a scatter plot for the number of PCs and the cumulative sum of PVE. This cube sum function, remember, will not change the dimension of a vector. It will keep track of the cumulative sum. For example, if you have a vector like 1, 2, 3, 6, etc., then the cumulative sum will be 1, 3, 6, 12. So it's after you apply the cum sum function, the length will not be changed. It's still a vector. Okay? And that is exactly what we need. We want to keep track of the cumulative sum of the overall PV for some number of principal components. So take a look at this plot. Turns out that, and I add a reference line, which is y equals 0.9, which indicates the 90% overall variance explained. Okay. So it turns out that you need to use at least 37 principal components in order to explain at least 90% of the variation in the data set. So namely, if I only want to lose 10% of information by reducing the dimension, then I need to use at least 37 principal components. Compared to the original width is this 972. So it's already very good compared to this many 773 to 37. It's already a big reduction actually. All right, so this is a cumulative PVE plot. It's very useful for us to determine. Alternatively, we can use this function. We first calculate the cum sum. So this, call it CPVE, cumulative PVE. And you can apply this which max function on this logical vector. CPVE is greater than or equal to 0.9. CPV is a vector of numbers, values, and then we compare it with 0.9. So the result is a bunch of, is a vector of true or false values. So you can imagine it's somehow like this, and all of a sudden, from the 37th number, it becomes true because the cumulative PVE is greater than 90%, right? 0.9. And then this weight max function will return the index of the first max value. of a vector. Um, false in R is equivalent to 0, and true in R is equivalent to 1. So the first max value is the first true. The index of the first max value is the first true, and the index is 37. Okay, so this is that's why we can use this function to identify the first time that the cumulative PVE is greater than or equal to 0.9. Right, so this is the first time the max value occurs. So it's 1. Yeah. All right. So that's all for principal component analysis. And very important thing is to really understand the strategy and the properties of principal components and how many distinct principal components can be created using a data set. It depends on the dimension of the data set, the shape of the data set. And also we learn how to calculate this PVE, proportional variance explained, and how to select the minimum number of principal components so that about like most of the information can be explained still.